Okay, so for lecture 14, this will be the topics, which is the introduction to Uniqueness Theorem. Okay, going to learn what is the Uniqueness Theorem is all about. And afterwards, we're going to solve, going to have a solution. We're going to learn how to solve a electrostatic problems by using the Laplace and Poisson's equation. Yeah. Okay, so that should be the main topics to be learned in chapter 6 or lecture 14. Yeah. Okay, so that will be the topics in lecture 14. The first one we're going to cover, going to learn about the uniqueness theorem. Yeah, and secondly, going to learn about the Laplace and Poisson's equation. So the reference for these lectures, you can obtain it from Sadiku, page 22 to 6 to 249. Yeah. Okay, and for your information, this will be the last chapter of electrostatic, as I mentioned just now. And our test 2, which will be held on the 27th of May, if I'm not mistaken, on Thursday. Yeah, hopefully you have, yeah, you have booked the date. Yeah, 27th of May. The topics that will be covered in test 2.
27th.
Yeah, 27th of May.
Okay, thank you.
So that will be the topics covered. Will start from lecture number 9. Yeah, lecture number 9. If I'm not mistaken, that is starting from the concept of gradient, yeah, potential gradient, yeah, and up to lecture 14, yeah, lecture 9 to 14, yeah. But the idea is that all of the fundamental aspects of Coulomb's law, Gauss law, so that concept still will be required, yeah, will be required in test 2, yeah. Okay, so exactly topics to be covered in the test 2 will be from lecture 9 to lecture 14, yeah. Okay, so hopefully this information helps you in preparing for test 2, which will be held by the end of this month. Yeah? Okay, so these are the objectives for lecture 14. Number 1 is to understand what is meant by uniqueness theorem. Okay, and number 2, secondly, going to calculate two important things. The first one is the electric potential, and followed by electric field. Yeah, electric field at a given point by solving the Poisson's and Laplace equation. Okay, so basically, if you base on this objective, the idea of this lecture 14 basically is to solve for the potential, yeah, potential, and afterwards we want to find the electric field, because the potential and electric field are interrelated with one another, as what we have learned previously in chapter 4. Okay, in which we have learned that both parameters here are interrelated from the equations of electric field. Okay, is equals to negative grad of V, or V equals to negative integrations of E dot df. Yeah, so these are the equations that can be used to relate the electric field intensity E and also the potential of V. Yeah, so we have learned this in chapter 4 of potential. So if we have the potential, for instance, yeah, if we know the value of potential, so we can use it to find the electric field by using the gradient concept. And if you know the value of electric field, we can use it to find the potential by using these basic equations, yeah, of potential. Okay, so that should be the objectives of lecture 14. So let's have a look on what is meant by Unionist theorem. But before that, these are the things that we have learned so far from chapter 2 on Coulomb's law up to now. Okay, so if you base on this slide, we can see that if you have a charge distribution here, yeah, charge distribution, you can have a point charge, you can have a line charge, you can have a surface charge density and also volume charge density. Okay, so in order to find the electric field intensity E, we can use the first law, which is the Coulomb's law. Okay, so this is learned in chapter 2. Okay, in chapter 2, we have learned this Coulomb's law. And afterwards, again, we can use the Gauss law to find the E field. This is learned in chapter 3. Yeah, but the limitation for the Gauss law is that the charge distribution must be symmetrical. Yeah, must be symmetrical, which is restricted to the case of infinite length, infinite area, and also on the spherical charge structure. Yeah. Okay, so that should be the Gauss law that we have learned in chapter 3. And in chapter 4, we have learned that from your charge distribution, we can use this equation, yeah, V equals to integrations of dq, yeah, dq can be in terms of rho LDL, for instance, yeah, okay, so an R capital or R small letter of R, yeah, so we can use these equations of potential to find, I mean, you can use the charge distribution value, the dq or rho LDL, for instance, or rho SDS or rho VdV. You can use it to find the potential, okay, find the potential, and afterwards, by using the potential gradient where we have E equals to negative grad of V, we can use it to find the electric field intensity. Okay, so this is what we have learned so far, chapter 2, chapter 3, and chapter 4. In chapter 5, we learned about the material, okay, specific on conductor and dielectrics. So in this chapter 6, we're going to learn about this, what we call as uniqueness theorem, yeah? So in uniqueness theorem, basically the idea is that we can use it to find the potential value. Yeah, you can use it to find the potential value, and to find the E field, we just simply use the potential gradient. Yeah. So, but the idea, the basic ideas of uniqueness theorem is that you need to have these two information before you can use the uniqueness theorem. Yeah. These conditions are, number one, we need to have the area properties. And number two, we need to have the information about the boundary condition. Okay, so if your problems, yeah, if your given problems do have these two important informations, the first one is area properties and also the boundary conditions, then only you can use the uniqueness theorem. Okay, so the Poisson, yeah, the Poisson and Laplace equation. Okay, the Poissons and Laplace. So this Laplace is not Laplace that you learn in in Epsilon system, yeah, because that Laplace is a Laplace transform, which is used to transform a signal from time domain to frequency domain. So this is another Laplace, but the same Laplace, the same guy, yeah, because he's a mathematician. Okay, so he invented a lot of ideas, a lot of mathematical equations, yeah. So this contribution by Laplace is basically used in field theory to find the potential. Okay, so we have this Poisson and Laplace equation. So both of these are categorized under the area properties. Yeah. Yeah. So the equations of Poisson and Laplace that we have mentioned earlier in our objective are basically parked under the area properties. Yeah. So your area will actually exhibit whether it will having a Poisson's equation or can be represented by the Poisson's equation, or your area can be represented by Laplace equation. Yeah, so we have two options. Yeah, so we're going to learn in detail after this what is meant by Poisson's and Laplace equation. But up to now, we have learned that this theorem of Unionist theorem is used to calculate the potential. Yeah, that's the idea of Unionist theorem, is to find the potential, and afterwards we can find the electric field. So in Unionist theorem, there are two informations that need to be supplied. Yeah, which are the area properties and also the boundary conditions. Yeah. Okay. So let's have a look what is meant by Unionist theorem. Okay, so this is from definition. Yeah, it said that the solution for electrostatic problem, in this case, is electric potential. Yeah, it means that the solution for potential or electric potential can be unique for a specified region if the uniqueness theorem is obeyed. Okay, okay, in which this theorem is said to be obeyed if it has these two information. The first one is boundary conditions. Secondly is the area properties. As I mentioned before, it can be represented by either the Poissons or Laplace. Yeah. Okay, which means that if we have this region, for instance, yeah, we have this region A, we have region B, for instance, and we have region C. Okay, and these three regions are bounded by its own boundary, for instance. Yeah, so it has its own boundary. So B has its own boundary, and C has its own boundary. Okay, so this theorem states that, for instance, yeah, if we take region B, okay, so the solution for the potential at region B, let's say we write it as VB, yeah? So the solution, I mean the VB, the potential in region B is unique, yeah? It's unique only to this particular region B, yeah? Yeah, if it has its own area properties and has its own boundary. So the VB is just bounded within the boundary of this region B. The same things happen is that we have a region C where it has its own boundary and it has its own area properties. So we're going to have a unique solution of potential in region C. The same things happen for region A. Yeah? So it means that the solution for a potential, yeah, is unique only for that particular region, which is bounded by its own boundary conditions and also fulfill specific area properties, either a Poisson's or a Laplace. Okay, so this is what we meant by Unionist theorem. Okay, hopefully you understand this clearly. So along the way, if you have any questions, please ask. Yeah? All right, so let us proceed with the formulation, yeah, formulation of Poisson's and Laplace equation. What is meant by Poisson and Laplace equation? So let's say we have a region, yeah, this region. So how can we know whether this particular region is it represented by a Poisson and Laplace equation? Let's just label this as region A, for instance. Yeah. So how can we know whether this particular region A is it fulfilling the equation of Poisson's or equation of Laplace? Okay, so to explain about these properties of this area of A, so we have to use the equation of first Maxwell, which is originated from the Gauss law. We have learned this in chapter 3, where we have the divergence of D equals to rho B. So we assume that this is a calculation or evaluation of the region of A. Yeah, so we are evaluating the divergence of D inside this region of A. Okay, so by evaluating the divergence of D equals to rho B, okay, we're going to have that D, yeah, if you assume, yeah, but if region A here is a dielectric, so supposedly the permittivity of this region A will be given by epsilon. Yeah, epsilon means that this is a dielectric, yeah, and we can have epsilon supposedly will be epsilon naught multiplied with epsilon R, yeah, which is a permittivity for a dielectrics. Okay, so we can then write that the D shall be equals to epsilon of E. Okay, and if you assume now that this dielectric is said to be homogeneous. Okay, what is meant by homogeneous? It means that if we take a point here, any point within this material, the value of epsilon will be the same. Okay, that's what we meant by homogeneous material. Yeah, so inhomogeneous is whereby the permittivity is not a uniform. Yeah, somehow if let's say we take this particular point here, so this point and this point might be not having same value of permittivity. So this is what we call as inhomogeneous material. Okay, so for the development of Poisson's Laplace equation in this particular case, we assume that the material is homogeneous. But in reality, in the real world, we cannot have homogeneous material. That's for sure. Yeah, that's for sure. Yeah, we cannot have a homogeneous material. We are going to have inhomogeneous material in our real world. Yeah. Okay, so back to this. So if you assume that the material of A, origin of A, is having a material which is homogeneous, so we can take out the epsilon outside the divergence operation. So we are supposed to have these equations then, yeah, epsilon multiplied with the divergence of E, and that should be equals to the rho V. Okay, and the E basically is equals to negative grad of V, which is from chapter 4, yeah, chapter 4. And we can have the equations to be looked like this, whereby this will give us epsilon, okay, of negative del squared, yeah, del squared of V equals to rho V. Okay, so we can have then the equations will be written as del squared of V will be negative rho V over epsilon. Yeah. Okay, so from these equations, we can define two possibilities. Yeah, the first one is if we consider that the region of A do have a charge. Yeah, charge of rho V exists inside the region of A. So if charge of rho V or the volume charge exists inside the region of A, so this region of A can be defined to be a Poisson's equation, or it can be represented by the Poisson's equation, in which the equation will be given by del squared of V equals to negative rho V over epsilon. Okay, so this del squared is also known to be a Laplace operator. Yeah, Laplacian operator. Yeah, and it's a coordinate dependence. Yeah, in which means that the Laplacian of V in this particular case will be depending on the coordinate that the coordinate of the problems given. Yeah. Okay. So we also call this as Laplacian. Yeah, Laplacian of V, for instance. Yeah, Laplacian of V. Okay, so it's known to be these equations or these terms. Yeah, where we have del squared of the V. Okay. So the second condition is whereby we assume that rho V equals to 0 inside this particular region of A. So if rho V equal to 0, so we can say that the region of A will be having a Laplace, or if represented by Laplace equation, in which we're going to have the Laplacian of V equals to 0. So these are two equations that can be used to represent the area properties. Yeah, whether it's a Laplace where rho V is not equal to 0, or the Poisson where rho V is not equal to 0, or Laplace where rho V equals to 0. So in your problems, in your area properties, you can use either the Poisson or Laplace to represent the area. Yeah. Okay then. Hopefully you are clear regarding this concept of Poisson's and Laplace equation. Yeah. Okay, then. All right. So this is what I meant just now regarding the Laplacian of a potential, which is depending on the system of coordinate. So you can have this from the textbook. Yeah, from the textbook you have this information. This is the equation for the Cartesian, Laplacian for Cartesian. This is Laplacian for the cylindrical, and this is Laplacian for the spherical. So please, you don't have to memorize this. Yeah. All of these will be provided to you. Yeah, you don't have to memorize. So you just need to know how to apply this Laplacian operator. Okay. So let's have a look on the solutions of the Poisson's and Laplace equation, in which eventually we can use it to solve the electrostatic problems, or in this case, we can use it to solve the potential, or finding the potential of the given problems. Yeah. Okay, so as I mentioned here in the first sentence, that the potential V can be calculated, can be obtained by solving the Poisson's and Laplace equation. Okay, so if we take a Laplace equation, yeah, for instance, if we represent the area by the Laplace equation, so we can have that Laplacian of V equals to 0, and for now we assume that the area can be represented using the Cartesian system of coordinate. So we're going to have the Laplacian of V in Cartesian system in 3 dimensions. Yeah, del squared V over dx squared, del squared V over dy squared, del squared V over del z squared equals to 0. Okay, but in our for this level, yeah, for undergraduate level, we just assume changes of the potential is in one dimensional. Yeah, it's one dimension only. Yeah, in one dimension only, which means that if you base on this equation, yeah, if in 3 dimension the V can be in x, can change in terms of x, V can change in terms of y, and V can change in terms of z. So the solution for this, we're going to have the potential to be in x, in y, in z. So yeah, so we can have the potential of V in 3 dimensions. But solving the potential in 3 dimensions is not easy. You need to use a computer programming to solve this, and it's not our level to solve this in 3 dimension, and also not in 2 dimension. Yeah, in 2 dimension, we can have it either Vxy, or we can have it as Vyz, or also we can have it as Vxz. Yeah, in 2 dimension, in 2 dimension. So for our case, we assume that the changes of V is only in 1 dimension. So it means that this equation now can be simplified. Yeah, can be now simplified to be changes of V only in 1 dimension, whereby we can have only changes of V with regard to X only, or changes of V with regard to Y only, or changes of V with regard to Z only. And selection of whether the changes of V with regard to X, Y, or Z will be depending on your problems. Yeah, so you have to select the changes of V very carefully. Yeah, so you have to know from the questions, from the problems, what are the changes of V? Is it in the X direction, or is it V is changed in the Y direction, or is it V is changed in the Z direction? So you need to understand, you need to know this clearly. Yeah, and this can be should be given in your given problems. Yeah. Okay, so for instance, if you say that if V is bigger in the X direction, so we can have it now that the del squared V over dx squared equal to 0. So to solve this, what you have to do, we have to integrate for the first time, yeah. So to first integration, we have dV over dx shall be equals to A, yeah, because if we integrate on the left-hand side, we're going to have dV over dx. If we integrate on the right-hand side, we're going to have a constant of A. And subsequently, if we integrate for the second time, we're going to have V should be equals to AX plus B. Yeah, so this is what given here in the given slide here. So we have the V basically should be given as AX plus B, in which the V is said to be varied in the X direction, and the A and B here, which are the constants, can be calculated or can be obtained by using boundary conditions which shall be provided in the problem. So that is why, as we have mentioned earlier, that this Unionist theorem need to have these two information. The first one is the error properties. Yeah, the error properties which enable us to find the general value of V. Yeah, and secondly, we need to have the information of boundary conditions, because boundary conditions will be very useful, or it shall be used in obtaining or in calculating what should be the constants of A, sorry, the variable of A and B. Okay, all right. Any questions so far on this Unionist theorem and also Poisson equation before we proceed further? Okay, no questions, yeah? Okay, hopefully you understand this clearly. All right, so let's have a look at this example number 1. Yeah, so we're going to start on the example to test our understanding on this concept of a Unionist theorem. So in this particular problems, we are given a perfect capacitor, capacitor structure, which is in the parallel plate structure, which is having a separation of 0.5 millimeter, okay, between the plates, and potential difference between the plates of it's given that rho v equal to 0 and epsilon is 4 epsilon naught between the plates. So if we can sketch the diagram, okay, so that should be the plate given in your questions. So given that in this particular plates, between the plates, we have the dielectric is having rho v equal to 0. The permittivity epsilon is given by 4 epsilon naught. Okay, and we are given that the potential difference between the plates is 50 volt. Okay, so we have potential difference of 50 volt between the plates, and the separation of the plates is 0.5 millimeter. Okay, I think that should be given by this A, given that Vy, okay, means that this is the Y, yeah? This is Y, yeah? So Vy, in which Y is from 0 to 0.5. So we need to find the Vy, which is Y from 0 to 0.5 millimeter, if potential at Y equal to 0 is 25 volt, and y equals to 0.5 millimeter is 75 volt. Okay, so it means that for this particular region, so this is the plate location, where this is the case, the potential at y equals to 0, so that should be 25 volt. And at this particular plate where we have y equals to 0.5 millimeter, the potential is 75 volt. Okay, so means that you need to find the potential within 0 to 0.5 mm in the y direction. So we need to find what should be the Vy in this dielectric or between the capacitor plates. So how to find the Vy then? Okay, so to find the Vy or to find the potential as what we have learned previously, we can, if we base on this slide, that we have learned. Okay, to find the potential, there are two methods. The first one is by using the V. You need to calculate the V, which we have the, or you need to use the integration of dq over 4 pi epsilon r. And secondly, you can use the Unionist theorem, whereby you must be given the area properties and also the boundary condition. So there are two methods to find the V, potential. But looking at these problems here, we are given straight away that the potential, the boundary condition is given. So this is the boundary condition, 25 volt at 0, y equal to 0, 75 volt at y of 0.5 millimeter. So this is the boundary conditions. And then you also given the area condition or area properties, whereby rho v equal to 0. So this is the area property. So based on this, it clearly shows that this particular potential can be calculated by using the uniqueness theorem. Okay, because we are given these two information, as I mentioned just now, we are given the boundary condition and we are given the area properties. Okay, so we need to select either to use the Laplace or Poisson, and since the rho v equals to 0, we have to use the Laplace, which states that Laplacian of v equals to 0. Okay, so from now we need to choose whether to apply the Laplacian in Cartesian, cylindrical or spherical, and clearly show that from these problems, your problem is in Cartesian. Okay, so we're going to have d squared v over dx squared plus d squared v over dy squared plus d squared v over dz squared equals to 0. So this is the equation from the Laplacian operator for Cartesian. But if we base on these problems, it shows that the potential of V will change only in the y direction, which is based on these problems. So which means that we can assume that there is no changes of V with regard to x, and also there is no changes of V with regard to z. So the changes of V is only in the y direction. So we can have then that d squared V over dy squared shall be equal to 0. And we need to find the V. So what we have to do is that we have to integrate both sides, left and right. So for the first integration, we're going to have a of y, I apologize, my mistake. So it should be a, okay, and for the second integration, we're going to have v shall be equals to a y plus b. Okay, so we have this equation in general, for the v. Okay, but this is yet to be done, in which we need to use the boundary conditions given here, which states that y equal to 0, v will be 25 volt, y equals to 0.5 millimeter, we're going to have v of 75 volt. Okay, so let us label this as number 1, this is as number 2. Okay, so from 1, we can say that 25, okay, you can have it as 25 volt shall be equals to A multiplied with 0 plus B. Okay, and we're going to have the B shall be equal to 0. Okay, so it means that B is 0 all the time. Sorry, not 0. My mistake. Sorry. It's 25, 25. Sorry for that. B is 25, based on the equation. And then we substitute B of 25 into 2. Okay, so we're going to have into this equation, using this equation whereby we are having the 75 volt shall be equals to A multiply with 0.5 times 10 power of negative 3 plus 25, and A shall be equals to 50 divided by 5 times 0, negative 4. And if we solve for this, you're going to have, this will be 10, and you're going to have 1 times 10 power of 5. So as such, we can write that the V basically will be 1 times 10 power of 5y plus 25. So that should be the general value of V, or the exact value of V in volt, which is based on the solutions or based on the applications of the given boundary conditions. Yeah. Okay then, so we have successfully calculated the potential. So, so allow me to write the V here in terms of y variable, okay, because your potential will be depending on the y, yeah, depending on the y position, yeah. Okay, any question for this before we proceed further? No, yeah? Okay, so if no, let us proceed with the part B of the question, which is to find the electric field plates, electric field between the plates. So, so for part B, because we need to find the electric field between the plates, so that shall be based on the equations of gradient, because we are given the V, or we have obtained the V, we can find the E field. From the equations of E field shall be equals to negative grad of V. Okay, and again, we need to use, because we know that gradient is to be based on the coordinate system. So use the gradient for the Cartesian, and by this we can write that the gradient should be negative dv over dy in the direction of y only. Yeah, because if you base on the v here, there is no variation in x or z. So we just have a variation of v with regard to y. So when we differentiate dv over dy, we are supposed to get negative 1 times 10 power of 5 direction of y, or simply we can have it as 1 times 10 power of 5 of negative of y. So that should be the V in volt per meter unit. So that should be the E, yeah, the E electric field intensity in the dielectrics between the plates, which is given or obtained to be 1 times 10 power of 5 in the direction of negative y. So if we base on this, if we can use a red marker to show the direction of the E field, so your E field should be directed like this, yeah. So that should be the direction of the E field. Okay, the E field density. Okay. Any questions for this then? Okay, if there's no question, I shall erase all of this because we want to proceed with question C here, just to find the capacitance per square meter, yeah? Okay, so need to find the capacitance now. Yeah, so we are given the same structure just now. This is 75 volt, this is 25 volt. Okay, so for capacitance, we know that from the equation, yeah, we know that the equation C from chapter 5 is given by Q over V. Okay, Q over V. Okay, can I ask one of you in this class, can I ask Sharik Faisal? Sharik Faisal, are you with me now?
Yes.
Okay, can you please define what is Q?
The charge?
Yes, so can you define it in this particular place? Where should be the charge Q then?
I think it should be right at the top, right? Close to the top. So between the plates?
Okay, charge Q basically if we base on, thank you Sharik, yeah, for your answer. So if we base on our lecture in chapter 5 before, so Q is a charge which can be calculated either on the positive plate or the negative plate, yeah, of your capacitor. Yeah, so if we assume that the charge here is rho s, for instance, yeah, so the Q basically is the charge on this particular plate, whereby Q shall be calculated by using the equation of rho s of ds. Yeah, that's how we calculate the charge of Q. And the same thing is applied if you assume the charge Q should be based on this plate of 25 volt potential. Yeah, so your charge will be based also on this equation, because we know that from the definition of capacitance, the Q will just consider the magnitude. We don't consider the charge polarity. Yeah. So let's say this is negative rho s. So it doesn't matter about the negative sign. We just care the magnitude of the charge itself. Yeah. Okay. So that should be the charge Q, which will be located on your conductor. Yeah, on the plates of the capacitor, which should be given by integration of the rho s ds. Yeah. So if you base on this equation, we can define it to be Q as rho s ds integration. Yeah, and V. What is V then? Can I ask Fatul Zaki? Fatul Zaki Hanafi, are you with me now? Fatul Zaki Hanafi? Okay. What happened? What happened to Fadila Rahmat? Are you in? No, also not here. How about Ihsan Aulia Rahman?
Yes, here, Doctor.
Okay. Can you please help me? What is the V here then?
The V is, I think, 50 volts.
Yeah. So what's the V then based on this diagram?
50 volts, Doctor.
50 volt. Thank you very much for your answer. Very good. Yeah. So which is the potential difference between the plates. Yeah. 75 minus 25 is with 50 volt. Thank you for your answer. Okay. So if you want to find the capacitance, the parameters that need to be obtained should be the rho s. Yeah, it should be the rho s. So you need to obtain the rho s in order for us to find the capacitance for this particular structure. So how to find the rho s then? How to find the rho s? So that's the idea, how to find the rho s. Okay, so to find the rho s, you have to go back to the basic boundary conditions that we have learned in chapter 5. Yeah, because we know that this is a capacitor. Yeah, capacitor consists of conductor. Yeah, conductor. This is your conductor then. Yeah, there's conductor plates. And this is your dielectrics. Yeah, that's your dielectrics. Okay, and we have learned in boundary conditions that when we have a conductor, we have a dielectric, for instance. Okay, we can say that if there is a charge of rho s on the boundary of this conductor and dielectric, we can write that the electric field will only exist on dielectrics, the E field, whereby the equation will be given by rho s over epsilon, yeah, in the direction of normal. Okay, you can refer back to chapter 5 lectures, yeah. Yeah, the E field will only exist in dielectrics given by rho s over epsilon in the direction of normal, in which the direction of normal will be away from the conductor. So if we base on these conditions, we can apply these ideas at the boundary between the conductor and the dielectrics, whereby we assume on the top plate here, your electric field will be in this direction, yeah, will be in this direction. Yeah, based on this, will be away from the conductor plates, and that E field should be equals to rho s over epsilon in the direction of negative y. Remember, yeah, because if we base on the given question, this is at 0. This is at 0, y equal to 0, and this is at y equal to 0.5 millimeter. So direction downwards for the E field means that it is negative y direction. Okay. And from the part B just now, yeah, from part B, we have obtained that electric field, yeah, electric field is given by negative grad of V, yeah, which is given by negative dV over dy of y. And from this, we have obtained that the E field is given by 1 times 10 of negative y, negative 1 times 10 power of 5, yeah, mistake then, direction of y, negative y, sorry, it's a negative y, okay, negative sign then, it's a negative y. Okay, so this is the equation of electric field inside the dielectrics. So basically, in general, the E field that we have obtained here and the E field that we have calculated from part B are the same. Am I right? Which means that if I label this as number 1, this is labeled to be number 2, So we're going to have 1, it should be equals to 2. And as such, we're going to have rho s over epsilon shall be equals to 1 times 10 power of 5. Yeah, and from here we can find the rho s straight away, whereby rho s shall be equals to epsilon times 10 power of 5. Yeah, and from the questions we are given that epsilon is 4 epsilon naught. So we shall write this as 4 epsilon naught times 10 power of 5 in coulombs per meter squared. So that should be your surface charge density. Yeah, on the plates. Yeah, on the plates. Okay, so from here we can use this surface charge density to calculate the capacitance straight away. So by using the rho s here, we're going to have C, yeah, should be 4 epsilon naught times 10 power of 5. So we just have integration of ds divided by 50, and the ds can be taken to the left hand side. Okay, so we're going to have C over ds, capacitance per square meter. You can bring the ds integration to the right hand side, and that should give us 4 epsilon naught times 10 power of 5 over 50. So please calculate this for me in the units of farad per meter squared. Yeah, because the question asks us to find capacitance per square meter. So capacitance per the area. Yeah, so that should be your capacitance per square meter for this particular problems. Okay, is that clear on this capacitance calculation? So the idea is to be based on what we have learned in the previous chapters. Yeah, so that's why I mentioned so many times in EMT that the things that we have learned will be used again and again. Yeah. Okay, so it's good if you can understand what we have learned in the previous chapters and previous topics, and that's the main reason why I keep on organize or do a quiz. Yeah, because I want you to have a constant understanding, constant review of this course. Yeah, not to study at the last minute. Yeah, so that's the reason why. Yeah, hopefully you understand this. Okay, any question on this example? Okay, if there's no question, let us proceed with the next example then. Okay, so these examples, we are given almost the same problems, but this time it is about the cylinders, yeah, conducting cylinders. We are given two infinite length, yeah, two infinite length, concentric, which means it's having same axis, yeah, same axis. That's why we call this as concentric. And conducting cylinders of radius RA of 0.02 and RB of 0.05 meters. Yeah, these are the radius of your conducting cylinders and located on the with axis on the z-axis. So if epsilon is 4 epsilon naught, rho v equal to 0 between the cylinders. Okay, so this is given the area properties, yeah, of your structure. And further on, we are given the boundary conditions, whereby at RA, the potential is 50, at RB, potential is 100. Okay, yeah? So the question now is find the V in the range of R from 0.02 to 0.05. Okay, so if I can sketch these problems of conducting cylinders, yeah? Okay, what is meant by conducting cylinders? It means that the cylinders is made up of a conductor, yeah? That's what we call this as conducting cylinders, yeah? Yeah, so which means that these cylinders and this cylinder are conductors, yeah? So given in these problems that we have this as RA, which is at 0.02, and we have this as RB, which is 0.05 meters, yeah? Given the area properties, epsilon equals to 4 epsilon naught, and then we have rho v equal to 0, yeah, which is the area properties between the cylinders. And further on, given that the potential here is 50 volt and potential here is 100 volt, yeah, because given here RA is 50 and RB is at 100. Okay, so the question now is to find the range, the V in the range of 0.02 to 0.05. Okay, so we need to find the potential here. Yeah, between 0.02 or between RA and RB. Okay, so if we base on these problems, yeah, so we can use the Unionist theorem to calculate the potential, yeah, because I mentioned in the previous example just now, we are given the boundary conditions and also the error properties. So by that, we can use the Unionist theorem to find the potential as requested here. Okay then, but first of all, yeah, we need to know whether this is to be based on the Poisson's or Laplace equation. And given that rho v equals to 0, so we need to use the Laplace equation. Laplace of v equals to 0. Okay, and we know that that should be based on the cylindrical system, sorry. Should be based on cylindrical. And for cylindrical, we know that the v, yeah, will be depending on r, radius, will be depending on the phi, the angle, and z, the height. So you have to choose what should be the variation of the potential in this particular problem. So evidently it shows that from this diagram, the potential will change according to the r, yeah, according to the radius. So as such, if we base on the Laplacian for cylindrical and considering only the r variation, we can write this Laplacian of v to be 1 over r, d over dr, or dv over dr, or dv over dr equals to 0. Okay, so this is based on the Laplacian of v, which is the changes of v with regard to the r direction only. Yeah, so we can now proceed with the integration for the first time. So for the first integration, we're going to have r dv over dr shall give us a constant. Then we have dv over dr shall be equals to a over r. And subsequently, for the second integration, we're going to have v shall be a ln of r plus b. Yeah, so that should be the general value of v in this particular region between Ra and Rb. So allow me to write the v in r variation. So we're going to have v in the r variations. Yeah, so it should be better. Okay. All right, hopefully you understand this on the calculation or v variation with regard to r, yeah, the radius. Okay then, so now we need to use the boundary conditions given to find the exact value of a and b. So we are given that at r equals to 0.02, b of 50 volt, at r equals to 0.05, b will be 100 volt, yeah? Okay, so we need to substitute these boundary conditions in the equations here. So let's say we have 50 shall be equals to a ln of 0.02 plus b. So we label this as the equation number 1. And then we have 100 shall be a ln of 0.05 plus b. So label as equation number 2. So what we have to do now, we have to solve these equations, these two equations. So let's say 2 minus 1. We're going to have 50 should be equals to a ln of 2.5. Yeah, so b will be then cancelled out. So a shall be written as 50 divided by ln of 2.5. Okay, so by using a calculator, so let me calculate this, the a. So using a calculator, going to have a shall be equals to 54.56. Yeah, so that should be the value of a. Right, so we substitute this a value in equation number 1. Yeah, so we're going to have 50 shall be 54.56 ln of 0.02 plus b. And afterwards, your b shall be equals to 50 minus 54.56 ln of 0.02. Okay, and the answer for b, using calculator, going to have this as okay, let me calculate this. Supposedly going to have this as 263.4. That should be the b, yeah? So as such, we're going to have v shall be 54.56 ln of r plus 263.4 in volt. Yeah, sorry, I need to write this as a VR again. Yeah, so that should be the VR, the variation of v with regard to r in the units of volt. Yeah. Okay. Okay, so we have successfully calculated the v in the range between Ra and Rb. Yeah. Okay, so next is to find the electric field intensity. So I think that should be no problem at all for part B here, in which from here, just based on the gradient method, E shall be equal to negative grad of V. Okay, and the gradient should be based on cylindrical system of coordinate. And knowing that the V is having just a variation with regard to R direction only, so we only have the gradient of V shall be written as negative dV over dr, yeah, negative dV over dr direction of R. And if we proceed with this differentiation, yeah, we are supposed to get as 54.56 divided by R in the direction of negative R, yeah. So that should be your electric field in the region between RA and RB. Yeah, so we have the potential and we have the electric field intensity. So for the flux density D, I think should be no problem at all. So the D should be equals to epsilon of E. Yeah, so the E field is given as obtained from part B just now. So epsilon, we just substitute the value of 4 epsilon naught. So that's going to give us the flux density D straight away. Yeah. Okay then. Any question for this example? No, yeah. Okay, so yeah.
I don't know how does the divergence square of V equals to 0 become 1 over dV dr times R dV. Then how it finally becoming R dV R equals to A.
Oh, is it this particular part? Is it?
Yes, the three convert
Okay, I think this is the only question, right? I cannot hear your voice after the question just now. Is it the only question that you have?
yes.
Okay. What's your name then?
Jasong.
Jasong. Okay, thank you, Jasong, for the question. Okay, so let us proceed with this. Okay, right. So you have to go back to the Laplacian for cylindrical. Okay, this is the equations now, yeah? This is the equation. Yeah. So if we base on this, we have Laplacian of V equals to 0. And as what we have mentioned just now, the variation of V is only regard to the R variation, yeah? So that can be cancelled out, yeah, because there is no variation of V with regard to phi and no variation of V with regard to Z, yeah? That's why we can cancel out these second and the third terms, yeah? Okay, so if we concentrate only on the first terms then, 1 over R, d over dr, R dV over dr equals to 0, yeah? Okay, so I do it step by step. So step number 1, we bring this to the right. So we can have d over dr, R dV over dr equals to 0. Then step number 2, we integrate both sides. We integrate d over dr, R dV over dr. The dr, I believe, yeah, I'm going to have 0 dr. So that will give us R dV over dr, and that will give us a constant. Okay, just so, yeah, hopefully you understand this. And afterwards, we can have, this is third step then, dV over dr should be equals to A over R. And for the fourth step, which is the integration, dV over dr, this is A over R, dr integration. So we're going to have V shall be equals to A ln R plus B. Okay, yeah? Hopefully it's clear, yeah, Jasong, yeah? Thank you for the question. Hopefully this will help others also. Thank you. Okay, then we proceed with the part B of the question. So allow me to erase all of these writings, yeah, because we need to use more spaces to explain D and E then. Okay, so for part D, which is to find the rho S at the RB, again, I have to re-sketch the conducting cylinders just now. Okay, so we are having, that should be your RA, sorry, the RA, yeah, sorry for that. And that should be your RB, right? And we know that this is at 50 volt, this is at 100 volt, yeah? Okay, the question is to find the rho S at RB. RB is at this particular region, yeah, at RB, which is at this region. Okay. Okay, so how to find the rho S here? How to find the rho S? That's the question, yeah? Okay, so we have calculated just now from our E field intensity just now, yeah? So we have calculated in this particular region that the E field there is equals to, if I'm not mistaken, yeah, so please correct me if I'm wrong, it is a 54.56 over R direction of negative R, yeah? So that should be the electric field in this particular region of between RA and RB, yeah, which is evidently given by part B. Yeah, you can prove this. Okay, and we know that the boundary conditions, yeah, again, I'm using boundary conditions problems. We have, this is a conductor, yeah, that's a conductor, and that's your dielectric. So if we can label this is a conductor, this is a dielectric, yeah. Okay, that is your RB, yeah, that's your RB. This is a center, z-axis, the center, that's your RB. Okay, so rho s is on this particular surface at the boundary between your, okay, so that should be the rho s, the charge density on the boundary between the conductor and dielectric. Yeah, and as what we have learned that the electric field will only exist in the dielectrics in this particular direction, in which this electric field can be calculated by rho s over epsilon direction of normal. Yeah, and because the direction is inward, so that should be rho s over epsilon direction of negative r, yeah, negative of r. Okay, so this is equation number 1, this is equation number 2, sorry, number 2. Okay, so we can say that 1 and 2 can be the same, yeah, but since we are evaluating at the radius of RB, so for equation number 1, we have to substitute r to be equals to 0.05, yeah? So at r equal to 0.05, we're going to have equation 1 shall be then equals to equation 2. So we have 54.56 over 0.05 in meter equals to rho s over epsilon, which is 4 epsilon naught. Okay, yeah. So hopefully you understand this flow of solving to find the rho s, yeah. Okay, because this equation of electric field is strictly at the boundary between the dielectrics and the conductor. Yeah, but the E field that we are given here or obtained here from part B just now is a general electric field which can exist between RA and RB. That's why we have the R variation there. Yeah, R variable here. So to be exact, at this boundary, which is at RB, we just need to substitute the value of R to be 0.05. Yeah, and as such, we're going to have that the rho s shall be equals to 4 epsilon naught, yeah, 4 epsilon naught divided by 0.05 multiplied with 54.56. So that should give us your rho s charge density in coulombs per meter squared, yeah, coulombs per meter squared. Okay, any question so far before we proceed further with part E, which is to find the capacitance per meter length? No, yeah? Okay, very good. So with no question, I think we can proceed with the part E now. Okay, so allow me to erase a few handwritings here because we have the spaces to write. Okay then, okay, if we base on this capacitance per meter length, yeah, which is capacitance in this region, yeah, because we have conductor, RA and RB radius, and in between we have a dielectrics. Okay, so capacitance is calculated here, yeah, between this particular conductor and this conductor and also the dielectric. So from the equations of capacitance, C equals to Q divided by V. Okay, we have Q should be equals to integration of rho s ds, and V is a potential difference between the inner conductor and outer conductor. And if we base on this value of potentials given, we can write that the V should be equals to 50 volt, yeah, 100 minus 50. Okay, and your rho s is to be based on this rho s, yeah, because we have calculated the rho s from the previous part D. So we're going to have 4 epsilon naught 54.56 divided by 0.05. Okay, and this integration of ds, yeah, because remember, yeah, this rho s is calculated on the radius of 0.05 just now. So the ds should be based on 2 pi of 0.05 multiplied with the length of L. Yeah, 0.05 multiplied with the length of L, and this should be then divided by 50. Yeah, so this ds, okay, if I can label this is to be base, yeah, this equation is based on the equations of 2 pi RL, the area of your cylinder, in which we are taking that the R is 0.05. Why 0.05 and not 0.02? Because remember, the rho s that you have calculated from part D just now is the rho s at RB, or rho s at 0.05. Yeah, so you have to be very careful on that selection of R, yeah? Okay, so we can cancel out few important things here. So this can be cancelled out. Yeah, so as such, we're going to have that this capacitance per unit meter, L can be taken to the left-hand side. We're going to have this as 4 epsilon naught multiplied with 54.56 multiplied with 2 pi divided by 50. So that should be your capacitance per meter, yeah, capacitance per meter in farad per meter unit. Okay, so please calculate the value on your own, yeah. Okay, any questions for these questions? I mean, for this example?
So, Doctor, in finding the rho s, can we use the RA in the negative direction of normal?
Sure, no problems. You can use it, no problems. But at the end, remember that the charge here must always positive. Yeah, so although you got rho s as negative from the body condition equation, but in calculating the charge Q, the rho s must be put as a positive value all the time. Yeah. Okay. Because there's no such thing whereby you can have negative capacitance. Capacitance must always be positive. Yeah.
But if you use the calculation of RA, then is the value of C will be different.
C by right should be the same. Should be the same, yeah, because this R and this R will be cancelled out similarly. Yeah, if you use 0.02, this and 0.02 here will also be cancelled out. Am I right?
Yes.
Yeah, you can try this first, yeah? You can try this first. If you have any problems, then you can discuss back with me. Okay, is it okay?
Okay.
Okay,
Yeah, okay.
good. It's supposed to be the same, yeah? Okay, thank you. Thank you for the question. The question just now is that what if instead of using the rho s at RB, you use the rho s at RA? And that's the question asked by your friend just now. So the answer is yes. And the answer is yes. Yeah, the answer, you can use it. Yeah, you can use the rho s at RA. But when you use the rho s at RA, if I can do it for you now, just for your information, yeah, that erase it now. Okay. So okay, that's your RA, yeah. That's your RA, and that's your RB. Okay. So you have learned just now that the E field is equals to 54.56 of R, direction of negative R. Yeah, and if you base on this boundary condition, yeah, we know that that should be the rho s then. Yeah, the boundary conditions between the conductor and the dielectric will give us the E field in its direction, whereby the E field here will be rho s over epsilon direction of R positive, yeah, because direction is towards the outward, so it should be positive. So then we need to equate this rho s over epsilon and this equation. So by equating these two equations, we're going to have rho s over epsilon to be 54.56 over R, negative, yeah, negative. Because this is positive R, this is negative R. Am I right? But since that we are calculating the rho s at RA, which is at 0.02, so we are supposed to get rho s to be negative 54.56 over 0.02 multiplied with epsilon. Okay, so as I mentioned just now, the rho s must be, although the rho s is negative, it's correct, yeah? Rho s is negative, but in calculating capacitance C, which is Q over V. Q must be positive. So if you go back to chapter 5, definition of capacitance, remember that we have Q written as this. Yeah, Q is a positive charge. Yeah, so we just care about the magnitude, not the sign. Yeah. So we can prove that afterwards, the charge obtained should be similar to what we obtained previously. Yeah, by using, whether you are using the radius at RA or radius at RB. So the value of capacitance must be similar or must be the same. Okay then? Okay, hopefully you understand this clearly on the example. Okay, we proceed with the next example. Okay, we are given these problems whereby we are having a volume charge density of rho v, which is negative 2 times 10 power negative 7, epsilon naught, a set of x Coulomb meter cube in free space. Let v equal to 0 at x equal to 0 and v equals to 2 volt at x equals to 2.5 millimeter. So at x equal to 1 millimeter, find these informations of v and also the ex. Yeah? Okay, so we are given in the x variation. So if I can have this as an x variation, this is at x equal to 0, the v equal to 0, x of 2.5 millimeter, the v equals to 2 volts. Yeah? And it's given that the rho v, which is in between this particular given boundary conditions, is negative 2 times 10 of negative 7 epsilon naught third of x. Okay, so if based on this, basically the rho v is not 0 anymore. Yeah, so we need to choose the use of Poisson's equation to solve for the potential inside this particular region, because the question asks us to find the v and the ex at x equals to 1 millimeter. So 1 millimeter is inside this region, yeah, because the boundary is between 0 and 2.5 millimeter. So in between here should be location of 1 millimeter. So basically you need to find what should be the v inside, yeah, so which should be the vx. Huh? Okay, so you can use the Unionist theorem, because we are given the area properties and the boundary conditions. Laplacian of v equals to 0. And since this is to be based on Cartesian systems, and furthermore the v is varied in x direction, so we can simply use d squared b over dx squared equals to 0 straight away. And if we jump to the final version of v, it should give us ex plus b. Yeah, sorry, my mistake. Not 0. Okay, it's my mistake, not 0. Sorry, we can simply put it 0. Because why? Because we are given the rho v. Yeah, we are given the rho v. Sorry for this, my mistake then. Okay, so the rho v is given by negative 2 times 10 negative 7 epsilon naught third of x divided by epsilon naught. Because why? It's given to be in free space. Yeah, from equation, Laplacian of b equals to negative rho v over epsilon. Yeah, negative rho v over epsilon, and because the region is free space, so we just have epsilon naught, and we have also a negative outside then. Yeah, negative here. Yeah, so we now have to proceed with the integration step by step, where we have d squared v over dx squared should be down positive of 2 times 10 power negative 7, cancel out, we're going to have x power of half. Okay, so we're going to have v dv over dx should give us 2 times 10 of negative 7, x to 3 over 2 over 3 over 2, and then we're going to have, plus a. Okay, and v shall give us 2 times 10 negative 7, x to 5 over 2 plus 3 over 2 times 5 over 2 plus ax plus b. Okay, so that should be the general value of v. So if we can write this v to be exact, it should be v which is varied in the x direction. Okay, so then we can use the boundary condition to find the a and b, where we have x 0, v 0, x of 2.5 milli, yeah, 2.5 milli, the v will be 2 volt. Okay, so you can substitute these boundary conditions into this equation. Supposedly, when we substitute this, you're going to get that B will be 0. Okay, and please work out for the value of A then. Yeah, please work out for the value of A. You can try to find A on your own. Yeah, and as such, you can find the V. You can find the V as a Vx of 2 times 10 power negative 7 x to 5 over 2 divided by 15 divided by 4 plus Ax. Okay, so please write this on your own. Find the A on your own. So that's how we find the Vx, and to find the Vx at 1 millimeter, just substitute the value of 1 millimeter into the x value. Yeah, and for the Ex, I believe you can do it on your own, whereby the Ex will be just use the E field first. Yeah, just find the E field first, based on the gradient method, where we have the E field to be based on the grad of V, and that should be based on negative dV over dx, direction of x, yeah, because your V is varied in the x direction only. So please solve for the V, dV over dx, and afterwards you can find the E field straight away. Okay, so I think it's quite straightforward. The difference between this example and the previous one is on this existence of the rho V, the charge distribution, in which we need to adopt the Poisson equation in solving for the V. Yeah, for the previous two examples, we just take that rho V is 0 because given the problems. Yeah, so we can we need to we need to solve for the V according to the given error properties. Okay,
Doctor.
Yes.
Doctor, for the Laplacian of V,
Yeah.
so the negative can be ignored, right? The negative sign.
Where's the negative sign then?
Negative 2 times 10 power of negative 7.
Because we have a negative sign here, negative rho V over epsilon. Rho V is negative, right? So negative is positive.
Oh, okay. Okay.
Thanks. Welcome. Okay then. So I hope that's clear for you. You have now understand this clearly, yeah, on the Uniqueness theorem, and hopefully, if you are given any problems on the Laplace and Poisson equation, you must be able to solve this. Yeah. Okay then. Let us proceed with this example. I think last example for today. This is basically to find the capacitance. Yeah, we need to formulate the capacitance for a spherical capacitor. This is I can say alternative. Yeah, alternative to the technique that we have learned in chapter 5. The end of chapter 5, which is on calculating the capacitance for a given structure. So just to show you that by applying the Unionist theorem, we can also solve, we can also formulate the equation for capacitance for any given capacitor structure. Yeah, so you have two options to find the capacitance or to formulate the capacitance formulation. But for this example, we are applying the Unionist theorem. We're going to show how this theorem can be used to formulate the capacitance for a spherical capacitor. Yeah. Okay, so let us start with the capacitor structure. So for a spherical capacitor, it should look like this, where we have the inner conductor, we have the outer conductor. Let's say we assume that this should be RA, and that should be RB lah. Yeah, so that should be our radius given, the inner conductor of RA radius, outer conductor of RB radius. So the inner plate is said to be grounded. So this is grounded. Okay, and the outer conductor is having a potential of V0. Okay, so in your case, if you're not given this information, what you can do is that you can assume the potential value, yeah, for your structure. So that what we can do, can assume, yeah, because as what we have mentioned earlier, in order for us to use the Unionist theorem, you need to have two information. The first one is the area properties. Secondly is the boundary condition. So what we did here is we define the boundary condition. We define that the inner conductor is grounded, which is 0 volt, and the outer conductor is having V0 voltage. It can be the other way around, whereby the outer is grounded and the inner is having V0, as long as we have a boundary value. Yeah, so that's the important thing. Yeah. And secondly, for the area properties, since you're not given any information about the rho V inside the dielectrics here, we can assume that the rho v equals to 0. So we have simplified it now. Yeah, we just assume that the Laplace or the dielectric, the region between the conductors, can be defined or can be presented by the Laplace equation. Okay, so for this, what we can do is that we know that from the equations of Laplace, where we have Laplacian of V equals to 0. Yeah, and this is for spherical capacitor, right? Okay, for spherical capacitor, and we know that this should be based on the coordinate systems. Yeah, and if we base on this formulation of spherical coordinate for the Laplacian of V, we know that the potential of V will vary in the R direction. So we can cancel out the theta changes, and we also cancel the phi changes of the potential. So we just consider the variation of the potential V with regard to R. Yeah, regard to R. Okay, so let us rewrite this equation now. So we have simplified to be just as 1 over R squared d over dr, R squared dV over dr equals to 0. Yeah, so if we integrate for the first time, we're going to have R squared dV over dr shall be equals to A. Then we have dV over dr shall be equals to A over R squared. And finally, we're going to have V shall be A or negative A over R plus B. Okay, so that should be our potential V. Yeah, potential V, which is the potential V change with regard to R, the radius of your spherical capacitor. Okay, so we managed to find the VR now. Yeah, because we need to basically from the if you want to use this theorem to find the capacitance, you have equations of C equals to Q over V, right? Yeah, Q over V. Okay, Q basically should be your charge at either plates here, whether it's RA or RB. So we can use integration of rho s ds to find the Q, and V here is a potential difference between the plates. Yeah, so we have defined just now that we have a 0, we have V naught. So the difference between these voltages will be V naught. Yeah, so just have it as V naught. So in order for us to calculate the capacitance, we are lack of this rho s. Yeah, we are lack of this rho s. So we need to find the rho s in this particular case. So how to find the rho s? So this is similar to what we have done in example 1 and 2 just now. Yeah, in which we need to find what should be the E field in this particular region. Yeah, yeah, and then from this E field information, we can compare it with the E field obtained from the boundary condition between conductor and the dielectric, and afterwards we can find the rho s, which is step is similar to what we have done in example 1 and 2. You can go back and see the steps of example 1 and 2 on finding the rho s, or finding the E field first, and afterwards find the rho s. So the rho s calculated shall be used here. Yeah. Okay, never mind. So let's say from here the VR, we can use this to find the E field. Yeah, find the E field from E field as a negative grad of V. So we can write this as equals to negative dV over the dr, direction of R, and then we're going to have this as a negative A over R squared, direction of R, or A over R squared, direction of negative R in volt per meter. Yeah, so this is the equation for the E field inside the dielectric between the RA and RB. Yeah, so this is the E field equation. Okay, so we need to compare this with the E field that shall be obtained from the boundary condition between conductor and dielectrics. For instance, let us consider the boundary at RB, for instance. Yeah. So we know that from boundary conditions, the E field will exist in this direction. Yeah, because that's conductor and that's dielectric. So the E field here shall be equals to rho s over epsilon, direction of negative R. Yeah? If we take that this material is having epsilon as permittivity. Yeah. Okay, so that should be the equation number 1, and that should be equation number 2. So we have to do now is that we have to compare, or we have to equate both of them. 1 equals to 2. Yeah, so we're going to have rho s over epsilon shall be equals to A over RB. Yeah, A over RB squared. Yeah, because we have learned that this is to calculate the field that we have calculated just now is at the boundary at the RB. Okay, so this is obtained from the left hand side is obtained from equation number 1, right hand side is obtained from equation number 2. But we substitute, or we write the R as RB because, as we have mentioned, the E field that we have calculated here is to be based at the boundary of RB. So from here we can write that the rho s shall be equals to A epsilon divided by RB squared. Yeah. All right then. So we are yet to solve this. Yeah, we are yet to solve this. Yeah, because we are lack of A. What is A actually? Yeah, what is A actually? So you have to find A. Yeah, you have to find A, in which you can find the value of A by simply use the boundary condition given here. Yeah, because given that at R equals to RA, we have V equals to 0. At R equals to RB, we have V equals to V naught. So you have to use the boundary conditions here to find the value of A. Okay, so let's say we use the first boundary condition at R equals to RA, V equals to 0. So from this equation here, we're going to have 0 shall be equals to negative A over RA plus B. Yeah, so we're going to have that from here. That should be the first equation. And second equation, we're going to have the V naught shall be equals to negative A over RB plus B, number 2. Yeah. So we can solve this step by steps. Yeah, in which we're going to have that if we subtract 2 to 1, we're going to have V naught shall be equals to A. Okay, we're going to have a negative 1 over RB plus 1 over RA. And then we're going to have that the value of A shall be equals to V naught divided by 1 over RA minus 1 over RB. Okay, so that should be your A. Yeah, that should be your A. Okay, yeah, so you have found out A now. So what you have to do now is that you have to substitute A in this equation of rho s. Okay, so by using this equation C, yeah, so we have rho s, which is V naught V naught divided by 1 over RA minus 1 over RB. That is your rho s. Yeah, and the ds will be 4 pi RB squared. Remember, yeah, because you are calculating this at this particular radius of RB. That's why you are using the ds, or the integration of ds, to be 4 pi RB squared, which is the spherical surface at R equals to RB. Yeah, and that should be divided by V naught. Okay, right. I think I missed something here. We have epsilon then. Yeah, we have epsilon there. Yeah, because A epsilon over RB squared. Yeah, sorry. We also have RB squared. I missed something then. Sorry for this. My mistake. Okay, rho s. This is your rho s. Yeah. Sorry. This is your A. Then we have epsilon over RB squared. Okay, this is epsilon over RB squared. Okay, that is your rho s in general. And then you have ds integration will be 4 pi RB squared divided by V naught. Okay, so RB squared and this RB squared can be cancelled out. V naught and this V naught can be cancelled out. So as such, we are going to have the equation of capacitance C shall be 4 pi epsilon divided by 1 over RA minus 1 over RB. Okay, so if we compare this capacitance, which is calculated based on this method, which is based on this Unionist theorem method, and the method that we have learned in chapter 5, Yeah, so we have these options now, whether you want to use this method or the method that we have learned in chapter 5. So which one is easier for you then? So it's up to you to decide. Yeah. But looking at these, the steps will be a bit longer as compared to what we have done in the previous chapter 5 lectures. But for chapter 5, remember, you have to define the electric field. Yeah, you have to find the electric field first, in which the E field can be calculated by using the Gauss law. But for this particular case, we just use the Unionist theorem to find the V, and from the V you find the E field, and afterwards you just use the capacitance equation to find the formulations for the capacitance. But the method or the formulation of capacitance should be the same, should be similar to what we have done earlier. Okay, any question for this example? Any questions? Okay, no questions at all. Hopefully you understand this clearly. Yeah. Okay. So I think I don't want to proceed with this example because there should be no questions of Unionist theorem in final exam. Yeah, because that's what we have mentioned to you in the earlier part of this EMT lecture, the first week of EMT lecture, that for electrostatic, it will only be tested in your test. It won't be tested in your final exam. Yeah. So for chapter 2 to chapter 6, it won't be tested. It won't be evaluated in your final exam. It will just be evaluated in your test 1 and test 2. Yeah. Okay. So I hope that you can try to do this on your own. Yeah. On this final exam, past year's exam example, also on this example here. Okay. So that's the end of chapter 6, and that should be the end of electrostatics. Yeah. So we have successfully covered the topics of electrostatics, yeah, from chapter 2 to chapter 6. Right. So this Thursday, we're going to start lectures on metastatic, metastatic, and it will start with the introduction to the metastatic field and also the sources, and also on the Bernoulli's law.